Somewhere beyond the edge of our solar system, objects wander alone through interstellar space. They drift for millions of years, shaped by forces we barely understand. Most of them pass unseen, silent travelers in a universe far larger than our instruments can fully observe. But sometimes, one of them enters our neighborhood. What if something crossed the orbit of our planets, not bound to the sun, not following the familiar paths we expect, and behaved in ways our models struggle to explain? What if we noticed it only briefly, just long enough to realize that it did not quite fit any category we already know? In mid-2025, astronomers detected such an object. It arrived without warning, moved with extraordinary speed, and followed a trajectory that pointed clearly beyond our solar system. It was given a simple name, 3I Atlas, the third confirmed interstellar object ever observed passing through our cosmic backyard. At first glance, it looked familiar. A faint glow, a hint of a tail, the signs of something comet-like. But as more data arrived, the picture became less clear. Its brightness fluctuated in unusual ways. Its structure appeared oddly organized. Features emerged that did not behave as expected. This was not a threat. It was not a message. It was something far more unsettling for scientists, a puzzle.
I'll show you the pictures that I took. There is a recent paper from Avi on the structured jets that he was noticing, looking at the Hubble pictures across the time period. This was not the picture I took last night. This was like probably a week ago. And I was looking at that picture and I saw a pretty long tail. I did show that live last night in the live stream. I'm going to show you that today. Let me zoom out. It's right there. You see that? I'll do it again. I'll go back this one. Right now, the comet is here, Jupiter is over here. And when I go 1 month, it's like right here, the distance.
Interstellar objects are rare, difficult to detect, and often visible only for a short time. They offer brief windows into environments far beyond our reach. And yet, 3I Atlas did not pass quietly. It forced astronomers to slow down, compare observations, and ask careful questions. What exactly was this object? Where did it come from, and why did it behave the way it did? This video is not about answers. It is about investigation, about following the data, the uncertainty, and the limits of what we know. Because sometimes the most important discoveries are the ones that remind us how much remains unexplained. The discovery of 3I Atlas began quietly, the way many astronomical discoveries do. Automated survey systems were scanning the sky, taking repeated images of the same regions night after night. These systems are designed to notice change, a point of light that shifts position, a brightness that was not there before. In July 2025, one such change stood out. Astronomers noticed an object moving faster than expected and along a path that did not resemble a typical orbit around the Sunday. At first, it was treated cautiously. Early detections are often uncertain. Instrument noise, background stars, or known objects can sometimes create false signals. But as additional observations were made, the motion remained consistent. Tracking data revealed something remarkable. The object was not looping around the sun like a planet or most comets. Instead, it was traveling along a hyperbolic trajectory. In simple terms, it was not bound to our solar system. It was passing through. That single fact placed it in an extraordinarily small group. Only 2 interstellar objects had been confirmed before. Each one had challenged assumptions in different ways. The appearance of a third was not just rare. It was statistically meaningful. To refine measurements, astronomers relied on multiple systems working together. Optical telescopes helped determine position and brightness. Radio observations added another layer of analysis. Tracking networks such as the Deep Space Network provided precise motion data, allowing scientists to calculate speed and trajectory with increasing confidence. What they found was striking. 3I Atlas was moving at a velocity far higher than most solar system objects. Its path suggested it originated far beyond the sun's gravitational influence, likely from another star system entirely. The direction it came from, combined with its speed, ruled out the possibility that it formed here and was later disturbed. As news spread through the scientific community, excitement was paired with restraint. Early data is often incomplete. Scientists know that first impressions can be misleading. Rather than speculate, teams focused on careful measurement. They examined its brightness curve, its shape, and any signs of activity. Was it emitting gas? Was it shedding material? Did it behave like a known comet or asteroid? The answer was unclear. Some features seemed familiar, others did not. The object resisted easy classification. That uncertainty made it more intriguing, not less. By the end of the initial observation phase, one thing was certain. This was not just another passing rock. It was a visitor from beyond our system, carrying with it information about environments we cannot yet explore directly. And it had only just begun to raise questions. Once the interstellar nature of 3I, Atlas, was confirmed, attention shifted from detection to understanding. Scientists began gathering as much data as possible, knowing that time was limited. Interstellar objects fade quickly as they move away, and each observation window can be the last. The primary tool for understanding such objects is light. Astronomers analyze how light reflects off an object and how it changes over time. This process, known as spectral analysis, allows scientists to identify materials based on how they absorb or emit specific wavelengths. In the case of 3I Atlas, the data did not provide a simple answer. Some observations suggested comet-like behavior. There were signs of outgassing, where material escapes from the surface as it warms. A faint tail was visible, indicating interaction with solar radiation. These features initially pointed toward a familiar explanation, but other details did not fit. The brightness of the object changed in ways that were difficult to predict. Instead of a smooth increase or decrease, there were irregular fluctuations. Jets appeared more structured than expected, showing patterns that suggested organization rather than random emission. Perhaps most puzzling was the presence of an extended anti-tail. Unlike a normal tail that trails behind an object due to solar wind, an anti-tail appears to point in an unexpected direction. Such features are rare and usually short-lived. In 3I Atlas, it persisted longer than models predicted. Radio observations added another layer of complexity. Signals were detected that did not clearly match known comet emissions. While none of these signals confirmed anything extraordinary, they also did not neatly align with expectations. Scientists compared data from multiple instruments. Optical telescopes captured structure, radio arrays searched for emissions, tracking systems refined motion estimates. Each dataset answered some questions while raising new ones. A major challenge was categorization. Comets from our solar system are relatively well understood. Their behavior has been studied for centuries, but interstellar objects arrive with unknown histories. Their composition may reflect entirely different formation environments. Could 3I Atlas be made of materials uncommon in our system? Could its surface structure have been altered by long exposure to cosmic radiation? Could internal layering explain its unusual jets? Each possibility was explored, modeled, and tested against observations. Some explanations worked partially. None explained everything. Importantly, scientists resisted the urge to overinterpret. Anomalies in data are not conclusions. They are starting points for further investigation. The trajectory itself also remained a point of interest. While it followed a hyperbolic path, subtle variations were closely monitored. Any unexpected acceleration or deviation could indicate internal activity or uneven mass distribution. By this stage, the picture was clear in one sense and unclear in another. The object was real, the data was solid, and yet it did not behave like a typical member of any known category. Was it simply unfamiliar, or was it something fundamentally different? That question remained open. When data resists easy explanation, science turns to hypothesis. not conclusions, but possibilities that can be tested against observation. In the case of 3I Atlas, two broad categories of explanation emerged. The first is the natural origin theory. Under this view, 3I Atlas is a comet or asteroid formed in another star system. During the chaotic early stages of planetary formation, many objects are ejected into interstellar space. Over millions of years, they wander until chance brings them near another star. Such objects may be fundamentally different from solar system bodies. Their composition could include unfamiliar mixtures of ice, rock, and organic compounds. Long exposure to cosmic radiation could alter surface chemistry. Repeated heating and cooling might create unusual internal structures. These factors could explain irregular brightness, structured jets, and extended tails. Models show that even small differences in composition can produce large differences in behavior. This explanation fits comfortably within known physics. It requires no new forces or technologies, but it does require accepting that our sample size of interstellar objects is extremely small. The second category of theories is more speculative. Some researchers have asked whether the object could be artificial in origin, not as a claim, but as a question. Could it be a probe, a fragment of technology, or something designed rather than formed? This idea gained attention because of features that appeared organized. The symmetry of some emissions, the persistence of unusual structures, the difficulty in fitting models. But extraordinary ideas demand extraordinary evidence, and so far the data does not require an artificial explanation. No confirmed signals, no clear propulsion, no behavior that cannot be explained naturally. Science does not reject such ideas out of discomfort. It sets criteria. What would we expect to see if an object were artificial? Do we see those signs? At present, the answer remains no. Importantly, the existence of uncertainty does not imply a hidden explanation. It reflects the limits of observation and the novelty of the phenomenon. Both theories face challenges. Natural models struggle to explain all features simultaneously. Artificial hypotheses lack direct supporting evidence. And that is precisely why 3I Atlas remains interesting. It sits at the boundary between what we understand and what we do not. It forces scientists to examine assumptions, refine models, and acknowledge gaps. The goal is not to decide what it is prematurely. The goal is to learn what it is not. And that process is still ongoing. As scientists continue to analyze existing data, attention has turned toward what lies ahead. 3I Atlas is moving rapidly, covering enormous distances in a fraction of the time it would take human-made spacecraft. In March 2026, the object is expected to pass near Jupiter. This event presents a rare opportunity. Jupiter's immense gravity acts as a natural experiment. As 3I Atlas approaches, scientists will carefully track its motion. Any deviation from predicted paths could reveal information about its mass, internal structure, or ongoing activity. If the object behaves as expected, following a smooth gravitational curve, it will strengthen natural origin models. If it deviates in subtle but measurable ways, new questions will emerge. Researchers will also look for changes in brightness, jet activity, and structure. Jupiter's influence could trigger additional outgassing or reveal features not previously visible. Timing is critical. The object is fading. As it moves farther from the sun, it becomes dimmer and harder to observe. Some estimates suggest that within months, only the most powerful instruments will be able to detect it at all. That makes this flyby especially important. It may be the last chance to gather high-quality data before the object disappears into the dark once more. The stakes are not dramatic in a cinematic sense. They are scientific. Understanding this object could refine models of planetary formation, interstellar travel, and the frequency of such visitors. Whether 3I Atlas confirms expectations or defies them again, it will leave a mark on how scientists think about objects beyond our system. And that is what makes the coming months so significant. 3. Atlas does not owe us answers. It passed through our solar system on its own terms, carrying with it the imprint of environments we cannot yet reach. What makes it important is not what it proves, but what it challenges. It challenged assumptions about how interstellar objects behave. It challenged models built on limited samples. And it reminded scientists that even with advanced instruments, the universe remains deeply complex. Throughout this journey, we followed the data, the discovery, the measurements, the anomalies, the theories. None provided a final explanation, and that is not a failure. Science advances through careful observation, skepticism, and patience. It advances by resisting the urge to declare certainty where none exists. Interstellar objects are rare messengers. They offer fleeting glimpses into other star systems. Each one expands our understanding, even when it leaves questions unresolved. As 3I Atlas continues on its path, future observations may clarify some mysteries and deepen others. The upcoming flyby near Jupiter may offer insights or raise new puzzles. So the question remains, was 3I Atlas simply unfamiliar, or did it reveal something fundamentally new? And if this is only the third such object we have detected, how many more pass unnoticed? Perhaps the real significance lies not in this single visitor, but in what it represents. A reminder that our models are provisional, that discovery often begins with uncertainty, and that the universe still has many stories left to tell if we are willing to watch closely enough.